Hi and welcome to the third lecture in the FOST course. This time I'm streaming live from Kalmar. I'm standing here speaking English in front of an all Swedish group of students, so it feels a bit strange, but we will do it in English anyway. The topic for today are data structures. Could you name a few data structures? Array is a data structure, but not really. Some other? A list, a queue, a stack, a graph, a tree. There are plenty of different data structures. We will take a look at a few simple ones today. But in general, these data structures are used when we want to handle large sets of data. For example, you are keeping track of all the students in a course or the measurements from an experiment, queues to get an apartment on our campus or the telephone numbers in Stockholm. Or in all these cases, we need to store a lot of data, and in most cases also often of the same type. It's a number of integers or a number of strings or a number of students. Different scenarios requires different data structures. Sometimes we want the data to be ordered. Sometimes we don't want to have any duplicate element. That means not the same element twice. Sometimes it's very important that the lookup process, for example, the telephone numbers, we want to have quick lookup to find a telephone number for a given person. But in general, it is important that certain operations X, Y, and Z are quickly handled. And depending on what data structure you are selecting, you will have different properties of them. So it is important to know about the different data structures, how they are implemented and how they work in order to select the proper one in different scenarios. Here are a few common data structures. List is the most frequently used. A sequential collection where each element has a position. In principle, it's like an array, but it grows on demand. You can add any number of elements as long as you have memory space available. A queue, you're adding things in one end and picking them out in another end. A stack, you're both adding and removing at the same side. Deck means double-ended queue. You can add and remove on both ends of a pipe. A set, the sets will be the topic of a lecture that we give later on. But in general, it is a collection that don't contain any duplicate elements. If you're adding the same student a second time, it will be identified and removed the second attempt or ignored the second attempt. A map is a key-value pair. You're adding pairs, key and value, and later on you can look up, give me the value for a certain key. A tree is one way of organized data. You have seen your file system, they're organized as a tree with a C colon as the root element, and then they have branches. It gives quick access. And a graph is another data structure. We have nodes and edges. For example, a road map with cities, then the nodes are the cities and the roads connecting them are the edges. This will be the topic of the third assignment in this course. In general, there are a few different data structures. You should know them. They are available in the Java library and in most programming languages. So you need to know about them in order to pick the correct one. For example, the telephone number. How would you store telephone number? Pick one of them. The set. Well, then they are non-ordered. Finding it might be a bit more tricky. And often, telephone number is a mapping from names to telephone numbers. So I would say that the map is a good candidate here. You are adding the name and the telephone number with the put method, and later on you can say, okay, give me the telephone number for a certain name. So a map would be suitable. A set would work also, but it's not as convenient when it comes to looking up the telephone number for a given name. The simplest data structure are all sequential. With sequential, I mean that they have a position. We have basically lined them up in an array, and each element has a certain position. So they are the sequential ones. The two simplest ones is the stack and the queue. A stack, I think of it as a pipe. I think of it as a pipe. We are doing all the operations on one end of the pipe. You can push an element, that means insert it, and when you push a number of elements, they go further and further in, and when you pop it, you're picking out the last added one. So they are also called last in, first out. That means the last added element will always be the first one to be picked out later on. Do you understand how the stack works? Think of it as a pipe, and we do three operations. Push means add one. Peek, or top is it called sometimes, means take a look at the top element but don't remove it. And pop means remove the first element. A queue is exactly what it sounds like, an ordinary queue. That means you're entering it in one end and leaving it in the other end. So the two operations here are called unqueue and dequeue. It means add it to the end of the queue and pick it out, the first one in the queue. They are the simplest ones since they have a very limited set of operations. Slightly more complicated are the deck and the list. A deck is a double-ended queue. It means we can add and remove element at both sides of the queue. And a list basically means add and remove everywhere. We can ask what is the element at position 1, and we can remove the third element and so forth. So this is the most flexible one. Anything you can do with a queue or something else, you can also do on a list. Why shouldn't we use a list? Why shouldn't we skip stack and queue? Because we can use the list for... List can handle all of these things. Any clever ideas? In general, if you have a general data structure that can do many things, it will not be as efficient. A Swiss Army knife is not as good a knife as an ordinary knife, because it can do many tricks, but it's not very good at all of them. The same holds with a data structure. In principle, it is possible to make it more efficient if it can only do 3 things, but it can do these 3 things very good. Also, a specialized structure provides a more precise model. If I'm reading your code and you have used a stack, then I understand what a stack means, and I know how it works. If you're using a list and treat it as a stack, it makes the code slightly more difficult to read, because you can do so many things with a list. So if you're using it as a stack, why don't pick a stack? So if you need a data structure and you only need it as a queue, then you shouldn't pick a stack. It makes your code somewhat harder to read. What is a data structure? Well, we are saying that the data structure is defined by a name, a type of data that can be stored, and a number of operation definitions. So for example, the name could be a string stack, the data type are strings, and the operations are, here I'm defining what operations we have. This is a data structure. You should notice that we are not saying anything about how it is implemented. It can be implemented using a linked approach or an array-based approach. It's not the part of what we mean by a data structure. A data structure is a queue, a list, but we are not specifying how they are implemented. So that's the reason why I was a bit reluctant to saying that an array is a data structure. It is more an implementation detail, a language construct. So it's not really a data structure, but it's tiny details. In Java, we are often using interfaces to define a data structure. By providing an interface like this one, I give it a name. By taking a look at it, I can understand that we are adding and removing strings. And also by specifying the method signatures and a bit of documentation, I have defined what we expect from the methods. So an interface is the most common approach in Java to define a data structure. You will see in the Java library that they have a list interface defining what they mean by a list, and they have a set interface and a queue interface. They have different interfaces specifying what they mean by a set and a stack in Java, and then they provide other classes that are implementing them in different ways. Different data types. We can have a fixed type, like in this one. We can have the object type, that means everything can be added to it. And we can have a generic type, that means we are deciding which type of data that we should store in it when we are constructing an object of the data type. Which one is the best? If you are about to implement a very efficient list, which one should you choose? You intend to use it to store students, but you might need it in some other cases as well. Well, the general idea is that a fixed type is stupid. If you put down a lot of work and implement a very efficient list that only works for students, then you have to come up with a new implementation the next time you want to work with employees or something else. So the general approach is to either use object or generic type, and nowadays they are recommending you to use the generic types. Then you can at runtime decide that this particular list that I'm creating here should store only strings. However, in this lecture we will do the opposite. We will do for integers only a list, but it's only to show an example in the simplest possible way. I will show how to implement this integer list interface. It only works with integers. We have an add method that adds an integer to the end of the list. We have add at that adds at a certain position, remove an element at a certain position, pick out an element without removing it in a certain position. We can also ask it what is the index of a certain element. We are asking at what position in the list can we find the element number 7 or something like this. It's all clear? It's a few methods, more methods here, but I will show two different ways of implementing it. One is based on arrays, and the other one after the break is based on linked implementation. And these are the two most popular approaches to implement the simple data structures, array-based and linked. So here is my class, array int list, that implements the int list interface. I decided that we need two fields. I must keep track of the current size, and I need somewhere to store my values. I store my values in an integer array. Initially, when we are creating an object of this class, I'm saying that the size of this array should be 128. So I have a constant size array where I'm storing my values. When I'm adding a new element to it, in most cases I am just inserting it at size, increases the size counter, so I'm inserting the new element into this array. However, at certain times, for example, for the first time when I have added my 128th element, then I recognize that the size is the same as the array size of this array, and then I need to grow. Otherwise, the next time I try to add something, I will be out of range of the array. So when it's full, then I call the resize method, and what I do down here is that I'm creating a new array twice as long as the current one, and then I'm copy all the elements from this one to this new one, and then I'm updating the field and saying that okay, now we should no longer use this one, we should use the one created up here. So I'm updating the field with a new and larger array. Did you get the idea? This is the most common implementation. Both in C# they have something called array list, I think, in C#. And in Java they have an array list. They work the same. I think in Java that the initial size is 1024. You always start with an array of size 1024, and when you're about to add your 125th element, it stops and takes these steps. Come up with a new array which is twice as long, and then it moves the elements from the shorter to the new one, which is twice as long. It copies all the elements here, and then it starts to use this one. So it doesn't grow every time you're adding something, it grows at certain points. Why not start with size 1? And then when we are adding a new element, we are creating a size 2 and size 3. Why make it, it's a waste of space in many cases here. Why not keep it as short as possible? Speed. In that case, every time I'm adding a new element, I would have to create a new array and move all the elements from the old one to the new one. It will be slow. Now we only have to do it at certain intervals, and these intervals actually get fewer and fewer since we are doubling it all the time. So this is the basic idea about array-based implementation, not only of lists, but also of queues and stacks. They are using all the same approach. They have an array that they are storing the value, but when needed, they make a larger version of this array and copy all the elements. Remove. How do you remove an integer at a certain position? Where do we have it? We have an array, and I would like to remove the element at position 7. Well, what I have to do is to locate this element, the one to be removed, and then take all these elements and move them one step in this direction. Then I have removed 7 from it. So that's what I'm doing here. First of all, I'm checking that the element is correct. That means it's larger than 0 and also smaller than size. If it is correct, then I shuffle all the elements one step forward. Starting from this position, the one that should be removed, I'm copying them one step like this. And then I'm decreasing the size like this. Did you understand it? How do we add one at a certain position? Add at. We would like to add 100 at position 17. Basically the same idea. I locate this position, number 17. I take all the elements here, move them one step in this direction, and then I insert 100 in this position. So that's, no. I thought I had that one as an example. Anyway, this is the idea of add at. You are making one space available by shifting them to the right, and then you're inserting it at that position. What is an iterator? When do you use iterators? Come on. An iterator is used when you want to iterate over all elements in a data structure. I think I have an example of how they can be used down here. Assuming that we have iterators available in the data structure, then I can create a new empty list like this, and then I'm adding a number of integers, and then I'm asking it, okay, give me your iterator. I got the iterator, and then I can, using this approach, as long as we have more elements, give me the next one. It is the standard approach to iterate over all elements. You are asking for the iterator, and you can use it using the methods has next and next. Has next asks, do we have any more element? And next means, give me a new element. Also, in the extended for statement, for each statement, as some of you would prefer it to be named. If you have an iterator, you can use it in this simple approach. You can say, for all integers in the list, do something with the integers in the list. So if you have an iterator and if you are implementing the iterable interface, it means that we have two options to traverse the list, using this approach or using this approach. You cannot use the iterator to pick out every second element or only half of them. They always give access to all the elements in a certain order. Why do we need iterators apart from this convenient approach? Why did they introduce iterators in the first place? Well, assume that you have a class called a course that describes a course here at the university. Inside this one, we are keeping track of all the students. And I would like to, as a user of this class course, I would like to say, give me all the students in the course. What would you do in that case? You could hand over the list where you have stored all the elements, but then you have broken the encapsulation. Then the user of the class can actually change the number of students in the class and remove a student. So what you are doing is that you are handing over an iterator over all the students. Then you are giving the user of the class access to all the students, but he cannot manipulate it. He can only read them, but he cannot update the set of students that we are keeping track of. So the first reason why we introduced iterators was to give access to data without breaking the encapsulation. They could see what students we have in a course, but they cannot change it. Let's get back here. If you take a look at my example, when I defined the int_list interface, I was writing that int_list extends iterable. This is a name of an interface that's available in the Java library. So in order to implement the int_list interface, you must implement the methods that I was lining up, but you must also implement all these methods. So an interface that extends another interface, they construct a new interface where the demand for the one who implements them is implement both of them. So it adds a few methods to be implemented. In this case, it only adds one method. So in addition to these methods, due to this construct up here, you must also implement a method called iterator that returns an iterator object. An iterator object is something that implements these three methods, and this one is optional. Often it's not implemented. So if I would like to implement the int_list interface, I must have a method that looks like this, and it should return something that looks like this. And it should be able, the one object that I'm returning, it should handle the two methods has next and next. So this is my approach. We are now inside my class array int_list. This is the detail where we are implementing the int_list interface, the iterable interface. I have the method here, and I'm saying, okay, in order to handle this one, just return one object of this guy. This is an inner class. It's inside this list. It is a class called list_iterator that implements the iterator interface. So when we are returning a new object of this one, we are fulfilling this criteria here. And this one, well, next means pick out the value from the array and increase the count variable. Has next means as long as count is less than size, and remove is not implemented. This is common. Remove is often not implemented. You can do it if you want to, but it's not expected from. This is the same approach as they have in the Java library. You can implement it, but you shouldn't expect it to work. Did you understand it? So this is how you implement the iterable interface. You must have a method like this, and you must create an object that works like this. The advantage is, of course, then we are giving these two properties. We can iterate over all the elements using nowadays this simple approach. So you will be asked to to construct an iterator for a queue, you can easily check that it works correctly by iterate over the queue using this approach. If you have done it correctly, it will work as you expect it to. Otherwise, it will signal some error. How about the break? A 10-minute break? Johan, did you hear that? Okay, let's be back here in 10 minutes from now. Before the break, I talked about array-based implementation of a list. We are adding more elements, and once in a while we are increasing the size of the array. Can you come up with disadvantages with the array-based? Now you understand how it works. Is it certain operations that you think are not very good? Well, assume I would like to use it as a queue, and every time I would like to pick out something from the queue, I'm removing the first element. What would happen in that case? Every time I'm removing something from it, we had to shuffle all the elements one step. So remove and add, especially when we are doing it in the beginning of the method in the array, they are rather time consuming because we have to move all the elements one step. In both cases, shuffle them right or left. Another approach to implement a list is to use a linked approach. So the disadvantage with array-based implementations, where am I? The disadvantages with array-based implementation is remove all elements has to be moved one step forwards, and add at all elements to the right must be moved one step backwards. And also a large portion of the array may not be in use. We have a somewhat waste of memory, although memory is not that important any longer. Anyway, another approach is the linked approach, and it's made of two classes. We have the list and we have the node. And the basic idea is shown up here, but I've also sketched it here on the whiteboard. The list class and the node class are the two building blocks. The user, the one who is using the list, he will only interact with the list class. The list class has the add method and size method and the remove methods. Internally, it keeps track of the size, that means the current number of elements, and it keeps track of the first element in this chain of nodes. It's the only one. It only keeps track of the first one. It's not called next, it's usually called head, the first one. So when we are adding a new element, we are traversing this list until we find null, that means no more elements, and then we are attaching a new node here, and this one then points to null. So we are storing the data in a chain of nodes, and the node class keeps a value and it knows about the next node in this chain. So every time I do some operation, add and remove, I'm locating something and I do some manipulations of this chain. So the add method, first of all, we are now once again implementing the int-list interface. This time we're using a linked approach, so I give the name to this implementation, a linked int-list. We are keeping track of the current size, and we know about the first node in this chain. The node class is very simple. It only keeps a value, and it knows about the next node in the chain. When we are adding something, we check if head is null, that means it's an empty list. Then we are just creating a new node and attach it to head. So the first thing we do when we have an empty list, then head is null. The only thing we do in that case is to create a new node and attach it to head like this. If it's not the first element, then we take the first node and then we are finding the last node by iterating over all elements here. As long as the next pointer is not null, we move to the next one. That's what we are doing here. As long as node next is not null, we are moving a node until the next one, until this one will stop when node points to this one. We have found the last node in this chain of nodes, and then we are attaching a new node to this one, like this. Did you understand the basic idea? You will see that I am traversing this list. Sometimes when I should remove, for example, this node, then I will locate this one, and then I will redirect this one like this. We are manipulating this chain of nodes all the time. So methods like get the element at a certain position, get an element at a certain position, well, we are moving this many steps forward. We are moving, this is at position 3. Then we are moving 3 steps forward until we point until this one, and then we are returning the element in this element. What is the index of the first node with a certain value? Well, we are traversing the chain once again. If we find the value, we are returning the current index. Otherwise, we continue until we have reached the end without finding it. And in this case, we return just -1 to say that we haven't found it. So all things add, remove, we are traversing this chain and change it in different ways. The iterator. Once again, we should implement a method that looks like this, and I do it by creating my new iterator, something that implements this interface. In this case, every time I create a new one, I take as my starting point the head node, and then next means give me the value, move 1 step forward and return the value. Has next means we have not reached the end of the chain. So each time we are picking out a value and we are moving to the next node, and has next, we are repeating this process until we have reached the end of the chain. Did you understand this one? Remove and add at are a bit more tricky. In order, assume that I would like to remove this one. I must locate the one before the one that I should remove, and then bypass, rather saying that next should not point to this one, it should point to the next one. So if I want to remove the 5th element, down here, I only move forward I want to remove the 5th element, then I call the next 4 times. That means I'm identifying the node which is before the one that should be removed. And what I do down here is bypass the one to be deleted. I'm saying that the node to be deleted is before next, and before next should now be the one after the one to be deleted. Do you understand here that I'm bypassing this node? I locate the node, this one should be removed. I locate this one, the one before, and then I'm saying that the one to be deleted is before next. The one to be deleted is before next. So this one is the one to be deleted, and then I'm saying that the new node that should follow before is the deleted next. So I'm saying that the new next value here should be the next one for the deleted. So in the second step, I basically drop this one. Do I have to remove this object, or will it stay there in memory all the time and be a waste of memory? How does it work in Java? If you have done programming in C or in C++, you know that you can allocate memory when you're creating new objects, but you should also keep track of removing elements, otherwise they stay in memory as a waste. It's not necessary in Java and also in C#. There's something called garbage collection. What is that? Once in a while when you're running a program, it stops for a very, very short time, and then it checks all the objects that are alive for the time being. And if no one is referencing them, they remove it. And once we have bypassed this particular node, we have changed this reference to be this new reference, there is no one referencing this one. So the garbage collector will identify that this one is not used by anyone and it will be removed from memory. If you're running a program like we do in this course, the programs only run for a very small amount of time and they are also do not consume any memory, then they don't do any garbage collection at all. Garbage collection only starts when they find a need for it. We start to have a certain amount of memory in use. Then they stop and it takes only a fraction of a second to do this cleaning up process. Okay. How would you do add at? I would like to add a new element at this position. Well, once again, I must locate the one before it and tell this one, we would like to squeeze in a new node in here. I had to locate the before and I had to redirect that this one should no longer point to this one, it should point to this one, and this one should point to this one like this. So it looks very similar. Add at. Find node before and then redirect them like this. So I think when you are programming linked data structure, it is a good idea to have a paper and pen and come up with a plan. How should I do this? Well, I locate this one and then I redirect them like this. And then you just transform this idea into a program. What is the disadvantage with this simplest possible linked implementation? Can you name an operation which is slow? Well, add. Go through the entire list and then add something in the end. And we are adding elements all the time to a list. And each time I had to go through the entire list until I find the final node and then I add it. So a simple improvement of the implementation is using not only a head but also a tail. We are keeping track of not only the first element but also the last element. So when we are adding an element, all we have to do is to attach it to the tail node and say, do a bit of updating here. Rather than stepping through and finding null, we can jump directly to the final node and do an update there. So this one is the one that we are recommending. Otherwise, add is very slow. I think I have it somewhere. This approach, I would like to access all elements in the linked list. I start at position 0, I ask it what is your size, and then I pick them out one at a time. This is also a slow process. Get, it moves forward. So first I found the first element, then I find the second element, and then I find the third. I restart from the head in every get operation. That's why when you are iterating over linked list, this one doesn't have this problem. It stops. When you're calling next, it just moves to the next one. It doesn't restart from the head all the time. So when you're iterating over linked data structure, you should not use this approach. You should always use iterators. Otherwise, you restart from scratch, from the head all the time. Another problem with the linked list is that each node only knows the next one. They don't know who comes before. So if, for example, you would like to print the list backwards, you will be in deep trouble. You will have to locate the last one, print it, locate the second last one, and print it. You always have to start from the beginning. So to make it more easy to navigate backwards and forwards in the chain, people are often using something called a double linked list. they are not only keeping track of the tail and the head, but the node also knows about the previous one. Then you can move in both directions along this chain to do different operations. However, now we start to have rather high number of different pointers here, so the remove operation, it's easier to make an error here. You are redirecting in the wrong way somewhere. But this is the approach that is used by Java in the library. They have a linked list and they are using this approach. So we have an array-based implementation and a linked implementation. Which one should you use? And when should you use one and not the other? So the advantage with the linked is that we don't have to shuffle elements in remove and add that. That means repeated are very slow in an array-based implementation. However, if we have a linked list and we want to remove this one, all we have to do is redirect this pointer here. And the same goes in the end. If we have a tail pointer, we can jump directly to the end of the list and just update something there. So if you use a list, and you will often do manipulations on both sides, especially in the beginning of the array, then you should use a linked list. We don't need any resizing mechanism. They grow all the time. That means we have no half-empty arrays that waste memory. So in practice, it might be that this one is slightly less memory consuming in certain cases. However, get is slow. If you want to pick out an element at position 150, you have no option in the linked list but to start from the beginning and actually move along the chain until position 150. What happens in an array? How do they locate an element? How do they locate an element in an array? Well, they know the address and they know that this is an integer array. We have stored it somewhere in memory, and they know the memory position of the starting point here. And if you would like to pick out the 50th element, they take the memory position here, and they know that integers are 4 bytes. So they jump directly to this position and picks it out. So picking out an element from an array is very quick. They just multiply the size of the elements with the position and jump there and picks it out right away. So picking out things in the middle of the list is much faster with an array list. In general, Java comes with three different classes that are implementing the list interface. They have the array list. It works basically as the one that I described earlier. They have the linked list. It works like this one. It's a double linked approach. And they also have one class called vector. It is array-based but thread-safe. What do they mean by thread-safe? If you're using different threads in your program, that means they are executed at the same time. It might be problematic if both threads are trying to access the array at the same time. They might collide with each other, these operations. So a thing that is thread safe makes sure that only one thread at a time can access the list. So when one thread starts an operation on the list, it puts a lock on it, preventing all the other threads from accessing it. So then the other thread has to wait until the first thread is completed, and then it can access it. This is good if you're using threads, but it's a waste of time if you're not using threads. So in general, this one is slower than this one. They are based, both of them are array based, but this one is slower since it put locks on it every time and removes the locks afterwards. So your option when you need a list in Java is to pick one of them. And if in doubt, use this one. Experiments, when they have looked at different programs, they have seen that if you should only use one of them, in general, this one is slightly faster. But if you will do a lot of these operations, then you should use a linked list. And if you should implement a queue that you will do, if you should implement the queue when we are only doing operations on the first node and the final node, then of course a linked implementation is much better. You don't have to shuffle any nodes, and you have direct access to the front via the head and to the back using the tail pointer. So usually if we are implementing a stack or a queue, we are using linked implementations. They have direct access to both ends of the queue. So, any questions about the linked implementation? If you just have this picture in your mind, you can figure out how the different operations works. And you can also figure out what is a time-consuming operation and which one is a quick operation. The same goes with the array-based idea. If you understand how it works, you will realize that adding and removing things in the middle of where we have to shuffle the elements is not a good idea. Then we should use the linked approach. So, when you are selecting data structure, you should first decide which type of data structure. You need a list or a queue or a stack or a set. But depending on what properties you need from the data structure, you are picking one of them. And then, which operations are most frequently used should be the next question. Then decides what implementation to use. Okay, I need a list, and then the next question is which one is most often used? Well, it's the add method. Then you can take the array list or something like this. Ask yourself 2 questions each time you decide upon a data structure. So, the exercise related to this lecture is for you to implement a linked queue. We have given you an interface. We are giving you the hint to use head and tail. That means you should have a list that knows about the first node in the list and the final node in the list. And when you're adding a new element, you should of course use the tail. You should not iterate over all elements like this. Questions? Okay, that's everything for today. We have a practical meeting, tutoring session for the Kalmar students here, and we stay in this lecture room. That's a basic idea. Okay, see you later.